Hello everyone. This is a video on the proof of the chain rule in calculus. So we know that the chain rule is as follows. We want to find the derivative of a composite function f of g of x. Its derivative is given by the derivative of f, which is f dash, but f dash evaluated at g of x into g dash of x. It may also be written as f dash at g of x into g dash x. That's the chain rule. For example, if you're finding the derivative of the sine of x squared, you could think of sine of x squared as a function whose outer function f is the sine function and the inner function is the x squared function, right? So f of x is sine x and g of x is x squared. So therefore, the f dash of x, the derivative of f, as we know, is cos of x. G dash x is 2x. And hence, we know that the rule, according to the rule here, right, that the derivative should be f dash at g of x into g dash x. This is going to be f dash, which is basically the derivative of f, which is cos f dash at g of x, and g of x is sine squared. G of x is x squared into g dash of x. F dash is cos, so cos of x squared into g dash x, which is 2x. So that's the derivative. Now, how are we going to prove the general result? This general result here. Okay, let's look at the proof. So, as every proof in calculus, as every proof of any of those shortcuts in calculus, the product rule, the quotient rule, even the chain rule is going to be derived from the definition of the derivative. And the definition of the derivative says that you have a function k of x, okay, its derivative is going to be the limit as h goes to 0, k of x plus h minus k of x over h. Okay, that's the derivative k dash of x. So here also in our case, we consider our function k of x as equal to f of g of x. Therefore, k dash of x is equal to the limit as h goes to 0, f of g of x plus h minus f of g of x over h. That should be the derivative of k of x, which is f of g of x, which is the composite function f of g of x. Okay, so that should be the derivative, f of g of x plus h minus f of g of x over h. Now, this does not appear to be anything that is in terms of the derivative of f or in terms of the derivative of g, those functions, right? We don't see anything like f dash of x, which is basically this, f of x plus h minus f of x over h. And we don't even see here anything that can lead us to, this. What we see is this composite function kind of expression. Okay, so how do we get to the proof? Well, okay. So like these things are missing here. I'm just telling you what these are, so I might as well erase this out. Okay. Okay. So what we are going to do here is to introduce introduce some expression that we are going to multiply by and divide by in all of this. So we are going to divide the whole thing by g of x plus h minus g of x and multiply by the same thing. We have to maintain the equality with the previous step, we have to multiply. Okay, and then separate this out into two limits. You can separate it out into two limits as long as both limits exist. So we shall see that both limits will indeed exist. So is equal to that multiplied by the second limit here. Now we can clearly see the second part is recognizable. We know this is equal to g dash of x. We know this. Okay. So this part is done. Now the only part remaining is to prove that this is equal to f dash at g of x. Okay, let's try to see if that is indeed the case. So this is still a question mark. This we know it is true, right? This part is g dash x, and we'll see what this part is. So this first part, only the first part, may be rewritten as the first part equals is rewritten as. We'll consider the g of x plus h minus g of x as equal to some h dash. So we know that h is very close to 0 as h, and we know that as h goes to 0, then g of x plus h will also approach g of x as long as g of x is a continuous function. And of course, we should assume that. We should assume that the underlying f and g functions of the composite function that we are trying to differentiate are both continuous and differentiable, of course. That is why the f dash and g dash exist. Okay. So if g is continuous, then g of x plus h also approaches g of x. It's very close. And we can assume that g of x plus h minus g of x is h dash is a small value. So h dash also approaches 0. Okay. So that was the assumption, which is true. So yeah, what's the first part equal to? So the first part here is equal to the limit, and we'll try to write everything in terms of h dash now. So limit as h dash goes to 0. G of x plus h is going to be equal to g of x plus h dash. So f of g of x plus h dash minus f of g of x divided by this denominator here, g of x plus h minus g of x, has already been assumed to be equal to h dash. So this is equal to h dash. Okay. And this entire expression does look like the expression of f dash of x, except that wherever x is supposed to be there, see, f dash expression is like this. Right? With the limit, of course. So this expression does look exactly like that, except that instead of h, we are using h dash, which is okay. H dash also approaches 0. Plus, instead of x, we are using gx. Right? Wherever x is there, we put g of x. So that is why this expression here is not exactly f dash of x, but it is f dash of x at g of x. This is f dash of x at g of x, like when x is g of x. Or you can also say this is equal to f dash of g of x, right? So that is it. This is the proof. We have proved that the derivative of, let's keep it here. graph. So we have proved that the derivative of the composite function f of g of x is equal to this first part, which was f dash g of x, into the second part. We already saw that was g dash x, and that is the chain rule. So that's the proof. Thank you, guys.